Welcome to lecture 30. So, let me just briefly go through what we have done and continue with normal forms. So, one of the things we did in any kind of computation is that we express the meanings as of the meaning of an expression as the value it reduces to. The meaning of an expression in piano arithmetic is just some representation of the number which is the value of the expression. The meaning of an expression in the lambda in the lambda calculus is a lambda term that contains no more beta redexes. In an applied lambda term, then it is something that does not contain either any beta redexes or any piano redexes. So, let us look at this thing, what might be called a model for meaning in some detail. So, let us go back to the beta reduction, and I will define a basis for a reduction as just the first axiom, right. So, this is just an axiom. What is an axiom? It is just some n-ary relation. In the case of reductions, an axiom is a binary relation which has a left hand side going to a right hand side. So, I can the set of all bold betas is essentially, this is essentially a rewording of the axiom of the first beta axiom for beta reduction, right. So, for all terms L and M belonging to lambda, this ordered pair which means that this application can reduce to this substitution is the basis of the beta reduction. Yeah. The normal terminology is to call it a notion of beta reduction, but I think since we use the word notion in a very general form, I will call it a basis of beta reduction. Many books will call it a notion of beta reduction. And what we do is, and your one step beta reduction is really what might be called the compatible closure of this set, right. So, what is the compatible closure? It is just that when you get these applications in some context, then the whole context reduces that way. I mean, this is something that we have done before, right. So, the compatible closure is really consists of these rules which we gave in the operational semantics, right. So, this first beta 1 is really the basis of the beta reduction, and the syntax of the lambda calculus allows only 3 possible constructs, or rather 2 possible constructs, but then application works, I can look upon either forms of the application as 2 possible constructs. And this, the one step beta reduction that you get by closing it over these 3 rules is what is the compatible closure, and that is the one step beta reduction, right. Okay. So, now, this one step beta reduction is just what might be called the compatible closure, and many step beta reduction is the reflexive transitive closure of the one step beta reduction, and the equality is just the symmetric transitive closure of the many step beta reduction. So far so good. So, the question of what exactly constitutes equality is something that has been subject to a lot of philosophical debate, and the main the consensus that is sort of emerged is, when you look at any forms of equality, it is important to look at it from an extensional point of view. Okay. So, by an extensional point of view, and this extensionality is a fairly fundamental philosophical concept which goes over starting from mathematics on to all branches of engineering, I mean including electronics for example, right. So, what is extensionality? Firstly, when are two functions equal? So, two functions f and g are equal. Let us for the purposes of argument assume that f and g are both unary functions. It does not matter really if they are n-ary functions, then I will just make this x a vector x. Okay. So, if f and g are unary functions, then f is equal to g if and only if for all values x, f of x gives the same value as g of x. Okay. So, this is what might be called an extensional meaning of an extensional notion of equality. I mean the effect of the function, if you look at the two functions as black boxes with an input port, then for all possible input values they give you the same output, then essentially the two black boxes are indistinguishable and one can be used for the other, right. So, that is extensionality. Okay. Now, so this is as far as functions are concerned. As far as sets are concerned, for example, it is exactly the same. The basic test that you can perform on a function regarded as a black box is that of supplying inputs and getting outputs. The basic tests you can perform on sets regarded as black boxes is to test for membership, give an input and get a yes or no answer, right. So, regardless, so two sets are equal if and only if they contain the same members. Okay. So, that is like testing, that is like looking at the set as a black box and not looking inside too deeply. For example, how exactly is the set represented, how exactly is the function represented, and so you are taking a black box behavior of the entity in question and you are trying to assuming that you can perform exhaustive number of tests, even if the number of tests you have to perform is countably large or even uncountable, assuming somehow that you can perform an exhaustive number of tests, you decide on that basis when two sets are equal, when two functions are equal and when two programs are equal. In fact, our definition of the semantic equality of let us say two programs is really based on an extensionality principle.
So, this extensionality same as equality?
No. Extensionality principle is just that you view an entity as a black box and test it exhaustively. Okay. So, that means you are, by extensionality what we mean is as opposed to what might be called its intention, right. So, extensionality is best understood if you understand what intention is, and intention is just the construction of the black box, the internal construction. Supposing you removed the cover on the black box and looked at its internal details. So, you could have this function f of x, its internal details are such that it is somehow of the form x square minus 1. You have this g of x which is of the form x plus 1 multiplied by x minus 1. So, the internal details in terms of construction are different for the two. However, since on testing they give the same results, you consider these two functions to be equal. On exhaustive testing for any value of x, the black box f and the black box g give you the same results. So, you consider them to be indistinguishable, and that is in fact what is also true of sets. It is true of, so if I can construct, so if you look at the internal construction of this set, is just that this is a set consisting of all multiples of 30, whereas this is a set which first you construct all even number the set of all evens, then you construct the set of all multiples of 3, then you construct the set of all multiples of 5, and then you take the intersection of all these 3 sets and you get some set. And what set you get, so the internal construction of this set is different from the internal construction of this set. The fact that they are both equal is something you can prove through number theory, set theory, and so on and so forth, but the essential fact is that their internal constructions are different. They are like two different, for example, two different electronic circuits which are somehow equivalent, right. And so the intention is something that we should not worry too much about. So when we are talking about equality, we are really worried about what might be called the extensional behavior. So if you, I mean, so well, the two favorite programs, the most favorite programs in semantics are these, right. So these two, I mean, their internal constructions are different, but they are really the same program. I mean, let me keep it like this. Yeah, one computes. Let's for the moment let's assume that we are talking about x being a natural number. So one computes y as a factorial of x by counting downwards, and the other computes y as factorial of x by counting upwards, right. I mean, so the internal construction of the two programs is different, but their behavior in terms of the actual output that you get, which is y, is the same for all natural numbers x, right. So that is, so this is the notion of equality which pervades essentially all branches of engineering, mathematics, and so on, right. So one of the things that happens with the beta reduction, so when we are talking about equality, one of the things that happens with beta reduction is the following, right. So consider a term L which does not have x as a free variable, and consider any term m, right. And now I can look at this term L applied to m, okay, and I can look at this term which is L with a lambda abstraction, and this lambda abstraction is applied to m, okay. In both cases, so this lambda abstraction when applied to m means that all free occurrences of x in this will get replaced by m, and since L does not have any free occurrences of x, what it means is you will just get L applied to m in a single step of the beta reduction, okay. And since from here you get here in a single step of the beta reduction, these two are actually equal by the beta equality principle, but they are equal for more important reasons. They are equal for extensional reasons. Regardless of whatever might be the argument m, both these black boxes L and lambda x Lx would give the same results for all possible arguments m, right. That is the important thing. They would both give the same results for all possible values of m, but within beta equality we really cannot prove that they are both we cannot prove directly without applying on m, we cannot prove that L is beta equal to lambda x Lx. So we infer the equality from extensional from its extensional behavior. typically a lambda term is meant to denote a function, and if the function for all arguments gives the same, if two functions for all possible arguments give the same values, then we have considered them equal. But however, our beta equality is actually not strong enough to capture that form of equality in isolation. Only so you can prove that, so we can only prove that L applied to any argument is beta equal to lambda x Lx applied to the same argument, but we cannot prove that L itself is beta equal to lambda x Lx, though of course it makes a lot of sense to equalize the two. So, the beta equality is not sort of powerful enough to take extensionality into account. And so, what we normally do is, if you are looking at the lambda calculus as a way of representing functions, is that we add an extra notion of reduction or an extra reduction basis, and that reduction basis is the eta rule, right. So, what this says is that it is important to realize one thing, that L applied to M is beta equal to lambda x Lx applied to M only if x is not a free variable of L. If x is a free variable of L, then these two are not going to be equal, because the free occurrences of x within L are all going to be replaced by M and you will get something different. L applied to M, okay. For example, if x is free in L and you apply L to M, then M is going to replace some other bound variable, it is not going to replace x, right. For example, if you take if L were defined as lambda y, x applied to y, okay, where x is a free variable of L, then L applied to M is going to beta reduce to x applied to M. However, lambda x Lx applied to M, okay, is going to reduce to well, L, all free occurrences of x in this term are going to be replaced by M. So, what is going to happen is that x is going to be replaced throughout. So, you will get lambda y M y, the whole thing applied to M again, okay. Right. And even though this might be, this reduces further maybe to this reduces further to M applied to M, but these two are not equal, this x applied to M and M applied to M are not equal, right. So, it is important to realize that only whenever x is not a free variable of L and you have a term of this form, then the effect of this term on all values of, on all arguments M is going to be the same as the effect of this term L on all values of M. So, we will define this notion of reduction, or rather this basis of reduction eta, and we will define its, well, a one step eta reduction as the compatible closure of eta over all lambda terms, the many step eta reduction, and equality eta equality as we did for beta equality, okay. And what we could do is on various, so we could also define now, supposing we wanted the extensionality principle actually to be used throughout, then what we could do is, instead of talking of just beta reduction and eta reduction in isolation, we could combine them both. After all, beta reduction is fundamental to us as function application. So, you could combine the two. So, you could take the two bases and take the union, and then correspondingly give a compatible closure, you will get a one step beta eta reduction, which means that in you either take a choose to do a beta reduction or an eta reduction. You can intersperse beta reductions and eta reductions in any way you like, and you do not have to follow any strict sequentiality. We can define the many step beta eta reduction as the reflexive transitive closure of the one step beta eta reduction, and we could define the beta eta equality. And the beta eta equality is really what we would think of as an equality which is compatible with our notion of extensionality. Okay. So, you have both function application and extensional equality, right. So, we will not look at we will not belabor this point. It is just important for us to know that there are various kinds of reductions we might define, and in fact this is not something new, because the piano arithmetic, though I did not actually mention it, we actually had two different notions of reduction, two different bases for reduction, and we had this language of expressions of piano arithmetic, and then so the basis of reductions in piano arithmetic were really these two sets. And what we actually used in the example of piano reduction, which I did not mention, is that we used first a union of these two, and we actually used, right. So, these are just the two definitions of addition and multiplication represented as binary relations, right. I mean m plus 0 is essentially m for all m belonging to n, and m plus the successor of n is the successor of m plus n, and m multiplied by 0 is 0, m multiplied by the successor of n is the sum of the product of m and n and m, right. So, what I had given is rules for the for piano arithmetic, and I did not actually specify, but this we were essentially using this without actually mentioning it. And next, and we also were actually using a compatible closure of this, which is a one step plus star reduction. And remember that if you gave these rules, which we omitted to give at that time because it was all taken for granted, it is actually non-deterministic. It does not matter how, I mean there could be more than one possible reduction, and then actually assuming all this implicitly, we actually did this derivation without actually using the rules, right. So, of which we took one possible execution sequence, right. So, but essentially in any form of computation, including let us say piano arithmetic, we have this, we have first of all non-deterministic sets of rules. Secondly, we have some notion of combining reduction basis so that you can apply things in arbitrary order, and we have the concept of a final value, which is a normal, which is what is called a normal form, right. So, let me look at so now what, when we are looking at normal forms, which, so what we will do is we will look at normal forms as a general notion. So, remember what we said about meaning, the meaning of a term is the value it reduces to. So, given any kind of reduction basis, a term in that language is an R normal form if it has no R redexes. I mean we can define plus redexes, star redexes, and we can define, for example, in the lambda calculus beta redexes eta redexes, beta eta redexes, and so on, right. So, you can actually we can actually talk about. So, if you look at the our original notion of meaning as the value that a term reduces to, in the piano arithmetic, it is really the value represented in that, in the form of this grammar of numerals, right. So, it is really so every number is represented either as 0 or as a successor of a number, right. That is the normal form, that is the value, the value, a representation of the value in the language, and given a basis. So, we in the lambda calculus too, we can talk about beta normal forms essentially as a term which has no beta redexes, that is the value of any term. So, you perform all the beta reductions, still you can find no more beta reductions, no more beta redexes, that is the value. Similarly, you can talk about eta redexes and eta normal forms, as a term is an eta normal form if it has no more eta redexes, and a beta eta normal form is one where you can neither find a beta redex nor can you find an eta redex, right. And essentially the computation terminates there, and that itself is regarded as a value of the original term you started out with. Okay. So, when we look at normal forms, the important question is in the lambda calculus is, does every term have a normal form? So, let us just look at beta reduction. So, does every term have a beta normal form? In the piano arithmetic, it turns out that every term does have a beta does have a plus star normal form, because all arithmetic expressions not having variables will reduce to a value. Okay. If you allow variables, then you should allow variables also in the basis language of expression, and then what will happen is you will get a normal form which is either a value represented as 0 or the successor of some number, or you will find it as a sequence of successors of some variable or a variable itself, right, if you allow variables into piano arithmetic and into the expression language of piano arithmetic. So, now in the case of piano arithmetic, you actually have all terminating computations, you always have a plus star normal form. But in the case of the lambda calculus, we had this horrible term called omega, for example, which does not have a normal form, because at every step of this computation you can always find a beta redex.
So, in piano arithmetic, if you have a variable x, then plus 0 dash x, so to what height does it do? Does it reduce?
Plus 0 dash x, that would reduce to, if you go through the beta reduction rules, it should finally reduce to plus x dash 0, and therefore it will also reduce to x dash. So, that would be the normal form. If you follow the rules systematically, it should reduce finally to x dash. Yeah, our rules for plus are asymmetric. So, I mean what it means is you will gradually be getting the successor from the right hand side argument to the left hand side argument. So, you should finally get a 0 on the right hand side, or if there are two variables, then you will get a plus expression in terms of the two variables. So, for example, plus of x y dashed would eventually just give you plus of x dash y, I mean that would be the normal form. Yeah. So, but you do have normal forms always. I mean you have some place, you have a step where you really cannot do any more reduction, whereas in the case of the pure lambda calculus, there are terms which always have beta redexes regardless of how many ever reductions you perform, and so therefore not every term has a normal form. Okay. So, the next question is, we have non-deterministic computations. So, now supposing instead of pursuing one form of computation, I pursue some other form of computation. I mean, I have maybe a collection of beta redexes and I have to choose one. I can choose one instead of the other. So, I have several possible computation sequences, several possible beta reductions possible. Then does supposing you have a term which has at least one normal form, one beta normal form, and it starts off with several possible beta redexes. So, that means you have several computation sequences. Do all those computation sequences yield the same normal form? Again, if you look at piano arithmetic, that is in fact the very basis of our notion of computation. I mean, you will find that all computations that you might do finally yield the same normal form, and we have grown up with it and we have taken it for granted, right. But it is an important question. I mean, if the lambda calculus is really trying to give you a fundamental picture of computation, then does every computation of a term which has a beta normal form, do they all give you the same beta normal form? And for this again the answer is no. So, if you take this term k, the combinator k is the projection combinator, right. I mean, if you remember, I had the combinator k is this combinator, right. So, it takes two arguments one by one and it gives you the first argument. However, because of the non-deterministic nature of beta reduction, there is absolutely no reason why I should apply k to x and omega and get back this normal form x. So, x is a normal form, right. I mean, there are no more beta redexes. On the other hand, this non-determinism allows me to do a reduction on omega as far as I want, and at any point I might decide to do the reduction of kx omega. Okay. So, there are a whole lot of finite terminating computations which all terminate in the normal form x, but there is also an infinite non-terminating computation where I have chosen never to apply k, the beta redex kx omega, but always apply the beta redex omega itself. Since omega itself is an application term, if I always choose to apply the beta redex omega, then I get a non-terminating computation, right. So, now what has happened is there are some fundamental reasons, there are some fundamental notions in which the lambda calculus is actually different from our normal understanding of computations in mathematics and so on and so forth, right. The next thing is, okay, so now you have non-determinism, you had non-determinism also in the piano arithmetic, there was no problem. The first thing was that the piano arithmetic always guaranteed a normal form, which the lambda calculus does not. The next thing is, even though there was non-determinism, the piano arithmetic actually guarantees that every possible computation yields the same normal form, which the lambda calculus does not. And lastly, supposing, so if the lambda calculus does not guarantee these things, then does it at least guarantee then that where two different computation sequences exist and which both yield normal forms, is it possible that a term can have more than one beta normal form? Right. In fact, if you look at the piano arithmetic, since all computations terminate, and it's even though there is non-determinism, they always terminate in the same normal form. In the case of so you cannot have two distinct normal forms. Okay. Now can a term have more than one beta normal form? So the fundamental question we are asking is, can a term have more than one meaning, depending upon how you execute the term? Okay. So if you look at, if you think of the notion of meaning as an intrinsic meaning, then what we would like in order for computation to be possible is that a term should not have more than one meaning. There should be an intrinsic meaning. If it has more than one beta normal form, it means that it has two different intrinsic meanings, and the meaning is dependent on the order of computation. Okay, which means that your notion of meaning is no longer a function from syntax to semantics. It is something very peculiarly concerned with the order of execution, and this is in fact true of many programming languages which have not looked at this problem in great detail. I mean, if you take this short circuit Boolean evaluation for Boolean operators like AND and OR, our intrinsic meaning of the Boolean operations AND and OR are that they are both commutative. But if you had an implementation with short circuit evaluation, then there is no guarantee at all that you will actually get the same meaning, right. The intrinsic meaning is that they are commutative, but in programs we know, especially in the presence of side effects, that if you flip the two operands of an AND, you can get different results, because the meaning is somehow not intrinsic enough to be determined by this semantics, but it is somehow dependent on the computation sequence. Yeah. So what is the fundamental property which will guarantee that a given term has only one intrinsic meaning, right, and that is the Church-Rosser property. So this is finally the only thing in which the lambda calculus actually does something that we expect. So it turns out that firstly, your first perception that does every term have a normal form, well, that is destroyed. If a term has a normal form, does every computation yield the same normal form? It is not clear, but if the condition is that if your reduction, your system of reduction is Church-Rosser, that means it satisfies this property, which I will expound on, then it is guaranteed that a term can have more than one, can never have more than one normal form. And in fact, that is a fundamental property of all these reduction systems that we are talking about, that they should be Church-Rosser, otherwise meaning is no longer a function of the syntax, meaning is then very highly dependent on execution. Yeah. Actually, it turns out that eta reduction is also Church-Rosser, but let us look at the Church-Rosser property in some detail. Yeah. The proof is rather long, so I will not actually do the proof here, but that is really the fundamental property. So now we can talk about this the Church-Rosser property for any kind of reduction, for any kind of reduction basis, right. So I will say a binary relation R, this is not necessarily a reduction relation, okay. This is any arbitrary binary relation on terms of the language. A binary relation R satisfies the diamond property, okay, if this diamond is satisfied, okay. That means if given that for all L, M and N, if it is true that whenever Lm belongs to this relation and Ln belongs to this relation, if it is guaranteed that you can, if it is guaranteed that you can find a P such that M and P are in this relation and N and P are also in this relation, then you would say that this relation satisfies the satisfies the diamond property. Yeah. So, it should be possible, is it possible given so for, now in the case of notions of reduction, what we are really looking at is this. So, a basis of reduction, now supposing instead of just being an arbitrary binary relation, if your binary relation was actually a basis of reduction. Now, this basis of reduction is Church-Rosser. If, well, from the basis of reduction you get the compatible closure, which is the one step reduction. From that one step reduction you do a reflexive transitive closure, you get a many step reduction. Okay. And if this many step reduction satisfies the diamond property, then you would say that the original basis of reduction is Church-Rosser or satisfies the Church-Rosser property, right. And this is in fact the fundamental thing you have to prove about any functional programming system that you design. Supposing you come out with a whole set of new operators which have got nothing to do with whatever is there in existing functional programming languages, then when you have and you claim that you have got a functional programming system, it is of no use to man or beast unless it satisfies the Church-Rosser property. And what it means is that if you take, okay, so what it means is that this diamond property should be satisfied by the many step reduction in that functional paradigm. Yeah. And so here is the theorem which has a simple inductive proof. If a basis of reduction R satisfies the diamond property, then its reflexive transitive closure R star also satisfies the diamond property. Okay, I mean, so if any binary, actually this is not necessarily a basis of reduction, any binary relation R satisfies the diamond property, then its reflexive transitive closure also satisfies the diamond property. I hope by now you know what the reflexive transitive closure of the relation is, right. It is like you take, well, you take in this case it is not like construction of, we are talking of relations and their reflexive transitive closure. So, that is not the same as the A star that we constructed for arbitrary sets. Okay. Here the R star is like this. So, you have a binary relation on a set, right. So, R is a subset, let us say, of set A cross A. Okay. So, this is a binary relation. So, it has various kinds of ordered pairs x, y and so on and so forth. Okay. So, now I can define R naught to be the identity relation on A. And what is the identity relation on A? This is to ensure reflexivity. So, it is just the set of all ordered pairs A such that A belongs to A, right. And given R naught, I can define R k plus 1 as being equal to R composed with R k plus 1 with R k. right. And what is this? This is just relational composition. So, what is relational composition? If R and S are both subsets, are both binary relations, then R composed with S is the set of all ordered pairs A comma C such that there exists a B satisfying the condition A comma B belongs to R and B comma C belongs to S. There exists a B in this set, B belongs to capital A. Right. So, now what your R star is just the union of R raised to k for all k greater than or equal to 0. So, what we are saying is how does our many step beta reduction go? It is just you start with a reflexive closure which is a one step beta reduction raised to the power 0, which just gives you the same terms, okay. It is a reflexivity condition, and then you compose it successively for k steps, and having obtained k steps you get k plus 1 steps by this composition. Right. So, this is just relational composition. So, the star is the R star there is a relational composition, a finitary relational composition. That means you do not allow infinitary compositions, right. If you allow only a finitary composition, and if R already satisfies the diamond property, then R star also satisfies the diamond property, and that proof is very easy. So, supposing you had L, okay, you have to show that if L goes to some m and it goes to an n in two different ways, okay. If L is related to, if L is R star related to m and L is R star related to n, then there exists some p which completes the diamond, okay. And if L is R star related to capital M, then what does it mean? It means that there exists a finite sequence of compositions. Let us say L is R star related to M implies that there exists some M such that L, the ordered pair L m is in R raised to small m, which means that I go through m compositions, L m1 is in R, m1 m2 is in R, m2 m3 is in R, and so on and so forth, and when I do the compositions I can find this kind of a path. So, what it means is L m2 is in R square, L m3 is in R cubed, L m4 is in R raised to 4, and so on and so forth, and L m is in R raised to m. Similarly, L n is in some R raised to n for some small n, and if this relation R satisfies this diamond property, then that what it means is that given L m1 and n1 which are all in the relation, this L m1 is in R and L n1 is in R, I can find a P11 such that m1 P11 is in R and n1 P11 is in R. So, I can complete this little diamond, and using the same reasoning inductively, what it means is that I can complete this larger diamond. First, I mean, let us take this slice. So, having constructed P11, I can use M1 M2 P11 to construct a common, something that completes another small diamond, which is, let us call it P12, and then using M2 P12 and M3, I can construct another small diamond which gives me P13 and so on and so forth. I can complete this entire slice, right. So, having completed this slice, I can now extend this slice to the next slice. So, there is an n step induction inside which there is an m step induction, okay, and I can find a P and M. So, what is the moral of the story? Given this fact, we can prove that beta reduction is Church-Rosser, that the basis beta of the reduction of beta reduction is Church-Rosser, provided we can prove that one step beta reduction satisfies the diamond property. If we can prove that one step beta reduction satisfies the diamond property, then the many step beta reduction also satisfies the diamond property, and therefore beta satisfies the diamond property. However, one step beta reduction does not satisfy the diamond property. Yeah, and here is the problem. Right. So, let me take this delta. This delta is actually, you remember omega, that horrible thing which goes on forever. Yes. So, the delta is just that part of that omega. Now, you take this delta and take any term m. Suppose m goes in one step to n. So, the basic assumption here is that we have assumed that m goes on one step beta to n. Okay. Then I consider this application delta m, okay, and in one step it can go to delta n, right, and then I consider this application delta n, which means that all occurrences of x here will be substituted by n by the one step beta reduction rule, right. So, in one step beta reduction this goes, by the way there should be a beta here, in one step beta reduction this goes to n applied to n. However, if instead of choosing the m goes to n reduction, if I applied this delta to m directly, then what I get is 2 m's, m applied to m, and now I require at least 2 steps either way to obtain n applied to n. I mean this and nn do satisfy the diamond property, because you can do this m goes to n beta reduction anytime you like, but which m are you going to first reduce to n is again non-deterministic, right. And so, in 2 steps I can go to nn, but this I cannot do this in one step. From I cannot reduce to nn in a single step, and that is where the bottleneck is, right. So, but however beta reduction is still Church-Rosser, so what it means is that such a simple fact cannot be used to prove that beta reduction is Church-Rosser. What it means is that, but we can use this example somehow. We define a new form of beta reduction in which parallel applications of these reductions are possible. Then okay, that means simultaneous, you can do the reduction across all possible beta reduxes that are immediately visible in one shot, okay, and consider that one shot reduction, which in a single step beta reduction will go over many steps, consider that to be a one step parallel beta reduction, okay. Then what you can show is that parallel beta reduction, when the star of that is the same as beta reduction, is the same as beta reduction star, and then you can show that parallel beta reduction actually satisfies this diamond property, and so beta reduction also satisfies diamond. So then that beta star, then that many step beta reduction therefore also satisfies the diamond property. as all that therefore also satisfies the diamond property, and so it is Church-Russell. Yeah, and the important thing about Church-Russellness is just this, that a term can have at most one normal form for any reduction basis R if that reduction basis is Church-Russell. It may not have any. Is in different computations you may never get a normal form, but if it does have a normal form, if there exists a computation which produces a normal form, then all computations which terminate would yield this same normal form, provided that basis is Church-Russell, and that is what the parallel beta reduction does. Yeah. So, I will stop here and go on to the type lambda calculus next time.